Hi, this is Jay Gant. I was going to talk about the problems on this page in the context of the lecture that I did. So the student only has prior algebra and pre-calculus and the rules that were mentioned in the lecture, which are the power rule, the sum or difference rule. The power rule is the first one here. The sum or difference rule just says that if you want to take the antiderivative of a sum or a difference of two or more terms, then you just antidifferentiate each term and add or subtract them. And then for the power rule, n cannot be equal to -1. Also, there was a rule that we could pull a constant that was not dependent upon x outside of the integral. So let's go ahead and start on. I'm just going to do problems that are indicative of the change in difficulty for each section. So, because I can't do all of them in the time that I have. So, part 1, letter D, the antiderivative of 3x to the 5 is 3x to the 6 divided by 6. So we just add 1 to the power and then divide by that number. And then we can reduce that to x to the 6 over 2. And then there's always sort of an understood plus c being tacked on there. And the directions are to find the antiderivatives with positive powers. But while we are evaluating, we want to leave everything in the numerator because we want it to look like the power rule. So in part E, we've got a negative power here, but there's nothing really wrong with that. We want the x term to be in the numerator to evaluate it. So we just add 1 to -2 and then divide by that number to take the antiderivative. To divide by -1 is the same thing as multiplying by -1. So that's the same thing as -5x to the -1. And then this is actually the answer, but the directions say to write the answer with positive powers. So, so there's an algebraic identity, or rule, that says that to change the sign of the power, move the term from the numerator to the denominator, or from the denominator to the numerator accordingly. So this x to the -1 can be moved to the denominator and changes the sign of the power. So these two things are the same using the algebraic identity given here, or rule that's given here. So this answer has only positive powers on the x term, so it's the answer that they want you to report. And then in part H, we've got roots, and there's an algebraic identity for this as well. So like the nth root of a is the same thing as a to the 1 over n. So a root is just a kind of power. And furthermore, the nth root of a to the m is a to the m over n. So using these two rules, we should be able to rewrite any root function as a power function. So this is the same thing as 2 times x to the -1/2. Sorry, positive 1/2. And then we just add 1 to the power and then divide by that number. So that's the answer. We can simplify that a little bit. To divide by 3/2 is the same thing as multiplying by 2/3. So we'll get 4/3 x to the 3/2 as our answer. And then for part O, we've got a negative fractional power, but we still just add 1 to -3/7 to get 4/7, and then divide by that number. So it's just the power rule again. Same pattern, I mean. And then to divide by 4/7 is the same thing as multiplying by 7/4. So that's our answer for part O. And then in T, all the problems should be like the ones we've done so far, but then in T we have something a little bit different, which comes from this algebraic identity. When you multiply like bases with different powers, you add the powers. And we just talked about how the square root of x is the same thing as x to the 1/2. And x is just x to the 1. So this term in the denominator rather, is x to the 1 times x to the 1/2. So that's the same thing as x to the 3/2. So we can rewrite the term in the denominator as x to the 3/2. But to evaluate these, to find the antiderivative of these terms, we need all of the x terms to be in the numerator. So we'll rewrite this again. We'll move the x to the 3/2 to the numerator and make the power negative. So now we've got something that we can evaluate using the power rule. So we just add 1 to the power to get x to the -1/2, and then divide by -1/2. So dividing by -1/2 is the same thing as multiplying by -2. So we get 12x to the -1/2. And then to write we want to write all of the answers with positive powers. So we'll just move this term back down to the denominator to get 12 over the square root of x. Alright, then in part 2, we're going to use all the things we did in part 1, but we're just doing the sum or difference rule. So I picked letter B to do, because B has 3 terms. So using the sum or difference rule, we just take the antiderivative of each piece and then add or subtract them depending on the signs. So the antiderivative of 3x squared is 3x to the 3 over 3. And then the antiderivative of the next piece is 4x to the 2 over 2. And then the antiderivative of -10 is -10x. Or we can think of that as subtracting 10x. So then the 3's cancel out here. You get x to the 3. The 2 and the 4 cancels out to make 2x to the 2 minus 10x. And then furthermore, we could factor out an x if we want to. But, I mean, there's really no reason to do that. Unless you were looking for the zeros of the polynomial. So yeah, we just take the antiderivative of each piece. Here we've got something that's already factored, but that actually makes it a little bit more complicated, because to use the power rule to differentiate this, we have to expand this multiplication. So expanding that, we get x squared minus 7x plus 3x minus 21. And that reduces to x squared minus 4x minus 21. And so the derivative of the factored term dx is the same thing as the integral of the factored term dx is the same thing as the integral of this term dx, because we've expanded the multiplication and they're the same thing. So this part 2f is the same as the one we just did. We just take the antiderivative of each piece and add them together. So it'd be x to the 3 over 3 minus 4x to the 2 over 2 minus 21x, which is very similar to the one we just did. But we get x to the 3 over 3 minus 2x squared minus 21x. And then in I'm not going to do part 4 because it's just multiple choice of ideas we already talked about. And I'm not going to do part 6 because that's in part 5. It's just multiple choice example of the problems that are in part 5. So in 5, I thought I would do A. So in this section, the student has not talked about integration by substitution or integration by parts. So since they can't use integration by substitution and they can't use integration by parts, then they have to, or given that that's the case, based on the information I've been given, then they need to expand all of these terms. So like in part A, x plus 3 quantity squared is x plus 3 times x plus 3. You get x squared plus 6x plus 9. And now you can take the antiderivative of each term, just like we did in the last couple examples, to find the antiderivative of this. So that would be x to the 3 over 3 plus 6x squared over 2 plus 9x. So you'd have to do every single one of these that way. So like in part B, you would expand x minus 5 quantity to the 3, take the antiderivative of each piece, and then it gets more difficult when you have negative powers. But hold on. So yeah, actually, you can't do all the problems in part 5 using just the power rule if you haven't talked about integration by substitution. Even if that substitution is trivial, ideally the teacher would talk about integration by substitution first, even if it was the case that the integration by substitution followed a linear pattern. That is to say, because it is technically an integration by substitution, even if the evaluation of that doesn't appear to be so. So the lecture page that I was given can only take you really up to J. Because once you get to negative powers, there really is no reason to expand it and use the power rule. Every single one of these, actually, you should be using integration by substitution. But this wasn't included in the lecture page that I was given, so I guess I'll just end the video here.